Almost starting, folks. If anyone's watching me on YouTube. Hi folks, just going to take another minute to get myself organized because I'm trying to get some nice, how do you put it? Nice and useful revision information in this lecture so that we have some stuff ready for you to check out. Best if statements. probably telling me, get started with that lecture, Charles. I'm desperate to have this knowledge. It's all very important. Oh yeah. What? Where is my Teams? Should be live on a few channels. That's going well. Make sure my Teams is available. I think I'm just about ready. Go back to my first page. Hope I don't have any embarrassingly terrible errors on the slides today. But you know, I do my best each week to not have any terrible embarrassing errors in the slides. If I do, you'll just have to tell me. G'day folks, I'm just going to start my recording and then we should be ready to go. G'day everybody, including everybody on the recording. Thank you so much for joining me live or recorded for COMP2300 week 6, the first lecture today. Oh, I should push something to the website. I'm just updating the slides a bit as we go. Make sure they appear on the website. Excuse me while I do some live web editing. Yeah, give that a dot, that'll do. I'm sure I haven't made any mistakes. We'll develop on main. Whoops, done something wrong there. Here's our talk for the day. Just make sure I got my correct screen open. And I do look like I'm speaking, which is good. Everyone should be watching me. I know I've got a good audience today. There's, I think, probably about 40 of you online between Twitch streams and YouTube. YouTube, as always, is one of the most popular platforms, which is, it's great that people are enjoying that. I like that I put in some effort and people respond to it by watching the lectures, which is what I'm really here to do. Open my general chat. I see there's some people having a good chat, like just starting with important assignment 1 hints. That should get people into the lecture. Team. So today's talk is officially titled Toolchains and Your Microbit, but we're going to spend, that's only a really small topic, and I'm really going to spend some time talking about the kind of admin stuff of the course so far, having a chat with you about how you feel things are going. We're going to do a lot more worked examples today, live coding on the screen. The toolchains in your microbit is a real topic, so make sure you pay attention for that little chunk, but it's only a little chunk. We're taking the last step of our coding and assembly and having a look at what a compiler might do for us, and trying to make that connection from the assembly you can know how to do now to compiled code, so that you'll then have seen in this last 6 weeks everything from digital logic, understanding NAND chips, going all the way up to compiled code from the output of a compiler, which is pretty cool to do that in 6 weeks, I think. So it's an exciting little thing. We mainly do it through demos and poking of a compiler, and not so much boring slides. So maybe it's a bit light on in terms of true information about compilers, but at least you should get a good idea about how these things work. Okay, let's get it started. This is the title. But first, before we do assemblers, compilers, and toolchains, we're going to do some admin time. We're going to talk a bit about the course survey, which has just come in. The results of that have just come in. We're going to talk a bit about assessments results so far and how to interpret them. And we're going to talk a bit about assignment 1. Speaking of assessment results so far, I just realized there's probably something you can't quite see on stream. So I'm just going to make sure that all of the assessments so far are enabled and available for you to view. Whoops, excuse me for not doing this before we started, but I had so many things I wanted to talk about, I kept putting extra stuff in the slides. What we should be able to see now is you should be able to see on streams all of your marks so far. So if you don't know how to do that, it's the same website as you used to update or to enroll in labs. And you should be able to see the mark from your lab pack, the mark from the quiz you did, oops, show mark, and the mark from your assignment 1 pre-submission. So if you want to check that now, please go ahead, and we'll be talking about it in a minute. And then the last bit of admin will be about assignment 1. The spoiler alert is that people have been dropping like flies with getting sick or getting stressed, and I just want to give you a little bit more time for everyone to do the assignment, and you will now get until Monday to do the assignment for everyone. Of course, if anyone has a particular issue where they need help, reach out for an extension, and we can still arrange that. But I really need to get started with the bulk of the marking on Monday day, so that's the extension that we can offer to everyone, just to give you an extra weekend if you need it. You don't need to use that time. You can use the time for other things if you need to. I always encourage everyone to make sure you know your whole schedule, not only be driven by deadlines, but try to be strategic about when you're doing the main bulk of work for your assignments. I know it doesn't always work like that. So that's the admin things we're going to talk about. Here's the course survey. I hope you did the course survey. And I guess if I had 50 people in front of me, 10 of them would have done the course survey, because we had about 20% of the students in COMP2300 doing the course survey. I think the fact that I just announced an extension has clicked with some people who are freaking out. Yeah, 20% of students jumped in on the survey, which was really great for a big course. That meant we got, well, it wasn't quite 20%, but we maybe got 80 or 90 responses, which was a really good number. There were 5 kind of choose a rating questions, which I've summarized on this slide, a visualization of these ratings. So this is a kind of plot which plots the kind of ratings people gave us, and generally the blue and dark blue ones mean we're doing things well, and the red and dark red ones mean we're not doing things so well. So the questions that were on these kind of rating scales were, broadly speaking, my questions get answered by the team. The assessment criteria are clear to me. The course activities are effective for me. I feel part of a community, and I can express my opinion in the course. So there were more words to that, but I just wanted to give you a quick overview of the responses. The great thing is that overwhelmingly, the vast majority of people said strongly agree or agree for all of the questions, which means that the course is, broadly speaking, working for them. You're getting the feedback you think you need. You understand the assessment criteria, you think they're clear. The course activities are effective for you. You feel part of a community, and you can express your opinions. Now, that's the majority, the vast majority. But I do want to acknowledge that there are people for whom the course isn't working for them. There are people who wrote disagree or even strongly disagree on some of these questions. And if you're one of those people listening to us right now, I just want to say that we are working for you too. Even if you feel that we're not reaching you right now, we're working every week. I'm working every week, the tutors are working every week, and we want to connect with you. So if there's some reason that we're not connecting with you and we don't know what it is, please reach out. We would like to hear from you. So if you're someone who feels that the course isn't working for you and you haven't been in touch with us, please do get in touch. I'm definitely concerned that there's one or two people or a little group who feel that they're not part of a community in this course. That's not just sad, because hopefully that it's a good community for everyone. That's our plan, is to have a great learning community that's really inviting and inclusive. But it's also a bit dangerous, because I worry about folks not feeling part of a community and therefore missing out on important learning experiences that you might be getting in your labs, working on lab work together, going on Piazza and chatting during the lecture. I know that there's some folks here watching me live who are chatting on Teams, and I think that they feel that they're part of a community. But I don't know who you are, because the survey was anonymous. I do know that I would like to hear from you. So if you feel like you're not part of this community, but you want to be, talk to us and we can work out a way to make that happen. So, like I said, most people, everything is working, and I'm really happy for that. Some people, things are not quite working yet, but we hope we can get them to work before we get too much further into the course. I'll talk now about there were 3 other questions where you had to write responses, and that's where I get some really interesting ideas and motivations for running courses. I love these questions where people write in how you feel about the course. First question, well, this one was a bit of an easy question for us, because what do you like about the course? We like to be told what we're doing well, don't we? I know that there's a lot of folks who say you like the tutors and you like me, which is great. I'm glad that you're watching the lectures and enjoying them. I really, really appreciate that, and the tutors really do. And if you're someone who really appreciates us as teachers, and basically if you're anyone who has any opinion on your teachers, I do encourage you to fill out the CELTs, which come out after week 10, I think. The student evaluations, which are more of a formal university-wide survey of learning and teaching. Fill those out and tell us what you think of us. Those, again, are anonymous. They come back and they count for us for something. If I'm trying to get something to happen in a course, I point to my CELTs and say, look, people liked it when I did this, so please let me do it more. I do use these CELTs as kind of my reason for doing things the way that we think are good in this course, in my teaching. So please give me your feedback in the CELTs. I look at it all, I use it, I remember it, I look back over them in dark moments where I feel bad about work, and I think, oh, but I did that thing, it was good, and people told me so. So it's really great to have that feedback. I know there are a lot of people who appreciate the labs. They think they're engaging and clear. I know there are lots of folks who really like the microbit. I like it too. There were people saying that they really like seeing the LED turning on, and they love learning about how computers work at a lower level, which is wonderful. It's a great experience. I'm really pleased that you have that experience and that you're appreciating it. I know there are people who enjoy learning to code in assembly. This would be news to some of my colleagues who think that assembly can only be terrible, but I know that it is enjoyable, at least in this course, for one time in your life, to have a go at assembly and really try to write some real programs in it. There's folks who say that they like how the labs and the assignments and the lectures all kind of connect and work with each other. Very much appreciated to get that feedback. That's something we try really hard to get to work. And there were folks who appreciated the quiz and said it helps learning without being stressful. Also much appreciated. Writing a quiz like that's a lot of work. So we appreciated that most people tried it and tried it lots of times to get a great mark. Someone said, I hope I'm not overstepping the line by quoting, but it's anonymous. This course is keeping me at uni, loving it so much. Well, that's so great. I'm really pleased to hear it. I do worry a bit about your other courses. Please make sure you're trying across all of your courses, not just COMP2300. But great that people are enjoying this course. What about things people have found hard so far? Well, people have found memory hard, overflow flag hard, carry flag hard, IT blocks hard, stack hard, and memory also, double hard. Memory is just hard. A lot of topics in this course are tricky, and particularly in this first 6 weeks, I think that getting on top of memory, dealing with how you use memory on a microbit is getting to be a bit of an important milestone for you to get the hang of. Some folks say that the reference manual is hard. I agree, very hard. Someone suggested that the reference manual needs a reference manual to understand it, which is a good point, but haven't got so much of a solution for that one. The reference manual, hopefully the index is its own reference. People have mentioned that the constraints of assembly are really hard, very tricky. It is very hard, big challenge to work within a very constrained language. Now this is a bit different. There are some folks who felt the labs and lectures were quite distant, and this, in contrast to the previous slide, some people felt they were quite close. That's okay, it's a big class, there can be different perspectives and different places in your learning journey and different things you come with when you start this course that help you understand these things. A few folks said that it has taken them some time to absorb the lectures each week. So hopefully this week I'm giving you a bit of a reprieve. You can basically be revising the previous lectures because the original content in this lecture is quite short. So you should be able to level yourself up this week and over the mid-semester break. And I really encourage you to use that time. Some folks say there's a big change from standard programming that you've learned in first year. I totally agree. Standard programming is quite different than assembly programming. You have to be prepared to break down topics even more than you used to in normal programming. A few folks saying that the creativity needed for the assignment was quite challenging. And I would say in particular, on the topic of creativity, many times I've met students who say, oh, I'm not creative, I can't do this. I can't think of something original. And I say, look, creativity is not something you're born with, it's a skill. Just like programming is a skill, just like understanding memory is a skill, just like typing on a keyboard is a skill. All of these things we have to practice, and the more you practice, the better you get at it. So I would say, look to the creative aspects of the assignment, inventing a kind of this new visualization on the LEDs. Think of that as a challenge, but go at it with a growth mindset, saying, I'm going to do this now, do it the best I can, and then next time I have to do a creative task, I'll be better. And I'll be better the next time after that. Because you will keep coming up to open-ended assignments in your education, particularly as you get past second year. There's more project-based assignments and open-ended work to grapple with. Some folks saying the assignment seems hard given the deadline. Hopefully I can help by giving this short extension just up to the Monday for everybody. I know that it would be great to have loads of time to do the assignment, but realistically I don't want you to spend that much time on it because it's only one assignment in this course. I want you to spend a decent but constrained amount of time and then move on to the next thing, because you've got another assignment coming up, you've got a mid-semester exam coming up, and I don't want these assessments to clash with each other. All of your assessments are just a moment in time, a sampling of your understanding, and I hope that you do the best you can, but it would be typical to have 1 or 2 weeks to do an assignment, and at this point you've got 3 weeks starting from week 4, but Of course, many people only got started in week 5 with their pre-submission, but I count that as when you started. So you've had lots of time. Most people end up doing these assignments in 1 or 2 days once they decide they really need to get it done. So I don't think a 2-month deadline or something wouldn't really help anybody. Excuse me. And final thing, people say, oh, there's limited information available online about ARM assembly programming, which is true. One of the things I really like about this course is that you can't just sit there in YouTube watching endless ARM assembly tutorials to try to understand the work. You have to do your own practice. Oh, unless you're watching my videos on YouTube, which of course is okay. ARM assembly programming is a bit more esoteric than, for instance, Java programming. There's a lot of courses in Java, not that many courses in ARM assembly. So lots of people know about it, but you're not going to find huge amounts of information. If you need help, ask on Piazza. And someone said everything. Well, yeah, that's a toughie, isn't it? I know there are some people who are struggling in the course right now. It's been 6 weeks of hard pace, hard march through all these topics. And there are folks who feel like they're behind. And there are folks who are behind, honestly. So what I might say is that often, if you think of your kind of actual capacity versus your felt capacity, or your capacity to do things might be just about to take off. If we think of a learning curve, you might feel like things are going really slow, but then you might be here, you're feeling really bad, and you're just about to shoot up in your learning capacity. So you might just be on this cusp of understanding the concepts and be able to do it. So keep trying. We have all the resources available in this course to help you. And it's a matter of engaging with it to just get yourself the next little step over time for your learning capacity to go up and for you to be a happy student. But of course, get in touch on Piazza if there's anything specific which we can help with. What would you change? It's always an interesting question, a bit dangerous to ask students what they'd change to a course, because people say, delete all the exams and make it really easy. Well, I suppose that would help in some ways, but you want your degree to mean something. So we do want to have challenge in courses so that we can learn and so our degrees are meaningful and that we can actually feel like we're engaging with the world, which is what we want to do. I had a long discussion with the tutors today about these ones, by the way. We're going to talk a bit more about how the lights work today. So that one we can solve. I'm going to tick ones I can solve with a green pen. People would like more engagement with their classmates, and I think this is part of where the community thing comes from in those quantitative questions. Maybe not group assignments in this class because they're a bit tricky, but we certainly can come in with some, I guess, more suggestions for group work during the labs, and I hope that people will get on board with those and come together. We've seen some great examples of, 3 people in a lab working together and sharing their ideas, coming up with a solution to tricky problems together, and that's the kind of thing I really want to encourage. So in future labs, starting this week, you can do it yourself as well. Try to get together with 3 people, not just one other person, but 2 other people plus you makes a real group. And try to attack one of the lab problems together, one of the tricky ones. Get together with those people. And then you get 3 heads together and you have different perspectives and different ways of solving the problems. And you might find a much more fun experience. People are looking for more details overall. We give a good level of detail in the labs. There's only so much we can provide. What I would suggest to those people looking for more detail is that every week I have a further reading page in the lectures. That's not further reading if you feel like it or if you've got free time. That's really like essential course material. If you want to understand things at a deeper level, get into that further reading. you're really only going to get a surface level understanding by listening casually to me on 2x played back on YouTube. You need to do some more of your own research and reading as well, if you need those details. So that I would say further reading. But you know, I always take the feedback. People want more details, great. I can give more details. Further reading, I mean. More quizzes. Well, you've got quiz 2 happening soon. The quizzes are a bit difficult to make, so we can only afford to make 2 in the class. Lab solutions. Well, that one I'm afraid is not going to happen. We don't provide solutions for the labs for a good reason, which is that if I give solutions out for the labs, they will be out forever. And there will definitely be folks who come into the start of this course with a full collection of lab solutions provided by their friendly upperclassmen or tutorial provider external to the ANU. It's realistically, I want people to be mainly fresh in the labs and do their own learning. What I can say is that I will keep providing more and more worked examples in these lectures. That's where I provide things. I do try to put the worked examples into the lecture slides as well as like one slide examples. That's my main place for storing the worked examples, by the way. I don't tend to have a repo that includes all of the worked examples. Some folks would like the labs to be easier and or harder, both easier and harder. So obviously we can't please everyone. We have to choose an amount of work, but we think we've struck a good balance for the majority. Posting demo code, that's sort of related to this one. More live coding, I'm going to do a lot today, so hopefully that will be related to that one before. I love doing the live coding, but it's a bit nerve-wracking to come into a lecture cold and just have to make something up. But everyone who's watching right now, please think about what you would like me to code today. I've got a few ideas, but you can think of some things to suggest. I'll help. Drop-in sessions. That one, I'd rather not schedule them because, I mean, I think there are folks where I can see that they're coming from a place of looking for more conversation with their tutor. And I know that there are drop-in sessions for some of our first year classes. COMP2300 does have longer labs, 3 hours, and it's quite hard to schedule them for the tutors. And all of your tutors are working incredibly hard every week to do their studies and tutor you in labs. So the amount of work they put in, I think I can't ask them to do more right now. I asked them to do a lot already just to cover the labs we've got. So I'm not going to add any drop-in sessions. If you would like to get involved with the student association that runs some study nights, that would be a good way to address that issue. I would help out providing tutors for those study nights if there's demand from the student association. Someone wants in-person lectures, or a few people mentioned in-person. Look, I love giving in-person lectures. My experience with giving in-person lectures is booking a room for 400 and having 30 people show up. That doesn't mean I'm not lecturing to 400 people. I'm lecturing to 30 people in person and 370 people who are watching it later on Echo 360. Now, what I find is that I can provide the best result for most of the students by lecturing to camera like this. This looks really good, this sounds really good, I get a great clear screen, I'm comfortable at home. I don't get to talk to folks in the audience one-to-one, which is something I miss. I loved doing in-person lectures and doing that, having conversations. But for the folks who are only able to watch this on video, including those remote in outside Australia, the online, getting a really great video is a priority for me. So I can either get a great video by doing it online, or I can get an average video and have a nice conversation. So I kind of have to sacrifice the conversation to provide the best online lectures for the majority. So I'm sorry, I wish I could have those in-person lectures sometimes, but it's a strategic decision to provide the best learning experience for the majority of students who do watch things online. So that's the survey. Of course, anytime you have thoughts, ideas, complaints, affirmations, send them through on Piazza. We're always happy to hear them and discuss them, any issues you might have. Where are we at with topics? We are exactly halfway through the topics in this course. We've done digital logic, ALU operations, memory operations, control flow, and functions. All of these topics are providing you with the tools for doing basic programming in assembly and understanding how what you do ought to work on a CPU in digital logic, in NAND gates. I know we haven't got every single detail in there. We've necessarily done a bit of a quick tour through some of those topics, but you're able to now write programs that are pretty complicated and have a good idea about how they might work on a CPU. Yet to come, we've got some more details. Data structures and interrupts and asynchronism are the two sort of final deeper parts about programming. Of course, we've done algorithms so far, but the other half of programming is data, really. And then interrupts and asynchronism is where we start to work out how to get a CPU to work with the world as input. We can use this stuff to do output. And you're doing that with your LEDs, but to do input, we need to work with interrupts and asynchronism. Then we have three more topics which are kind of like, well, these are higher level computing, high level, and then a sort of visit back to low level as the final topic. And so architectures kind of brings us back to what we did in week 1 and 2 with ALU operations and digital logic, connecting those together. And that takes us to week 11, and then we've got week 12 as a revision week, much like this week, week 6. What about assessments? Where are we at? I will say this is the critical assessment right now is this one. And that one has been extended to Monday, 4th of April, 9 a.m. Canberra time. So not 23:59, you just get the weekend and then we need it on Monday because I have to fork and clone those assignments for the tutors to mark in good time. The next assessment after that is the mid-semester exam, and that one is coming up at the end of April, 22nd, in week 7. So that one, make sure you're studying over the mid-semester break and practicing all of those 6 topics we've covered so far. So these assessments are now completed and the marks have been released on FAIS. That's 3.5 marks. Now I would like you to go and look at your marks and add them up. If your mark is less than 1.75, that's a warning sign. Okay, that's half, 0.5%. That means at the moment you're tracking to not pass this course. I know there are students in that situation. Not a huge number, but a collection. I'm going to add some more exclamation marks because really these 3 assessments are very accessible and most students were able to get full marks over those 3 assessments, which is great. It shows people are engaged and doing things at the level we expect to complete the rest of the course with a good result. Less than 1.75, that means you're not doing what we expect to complete the rest of the course with a good result. So it is census date this week, and I would hope that people are taking the time to think about their performance in the course. The vast majority of people are doing fine, but there are a collection of folks who haven't been engaging with some of these tasks. I know there's some people in this group because they've had extensions that I haven't covered yet, but they can know themselves that their mark isn't accurately reflected yet, but we'll fix those up this week for them. So yeah, do look at those 3 marks. That's your feedback, important feedback to know how you're going with this course. If it's less than 1.75, how you're going with this course is not good. We really need you to be putting in more sustained engagement with the assessment tasks to get a good result. Okay, sorry to have to say that stuff, but I know there are people who need to keep up, and my preference is for them to make good decisions for their education. Assignment 1, more info about assignment 1. What do you need to know to do assignment 1? We haven't even got to the content of the lecture yet, right? But I'm giving you the keys to the kingdom here. These are the absolute amazing hints. The assignment is this, our U program, should be your program. Your program must use the LEDs to create a light show that changes over time. That's the basic assignment spec. What do you need to do this? You need to know how to blink any LED on the microbit. You need to know how to blink any LED on the microbit. Now, that is Lab 4 knowledge. If you don't know how to do that, you need to go back to Lab 4 and do those exercises right now. And if you can't figure them out, you need to ask your tutor about it. Now on Piazza or this week in your lab, your tutors are prepared to help you with this knowledge, how to blink any LED on the microbit. Second need, how to scan across columns and rows quickly to display an image on the LEDs. That's Lab 5 knowledge. I know a lot of folks missed that one because Lab 5 was busy doing their assignment pre-submission, and there were people who missed the lab for various reasons. But that also is crucial knowledge, lab knowledge. If you don't know that, I'm going to talk to you about it quickly now, but also try it out now and talk to your tutor about it. It's one of those exercises in Lab 5. Where was it? Sound and light. Task 3, draw a picture. Very simple task, but a bit tricky. Requires you to think about how to approach turning on multiple LEDs at a time. So, and overall, this is a want, not a need, but I want you to have, before doing this assignment, or while you're doing it, excellent knowledge about memory, control flow, and functions. And we're going to revise that a little bit today so that we're all on the same page. That's all the labs and lectures so far. So please, please, please make sure that you're up to date with the lectures. This stuff does help with the assignment. I've started to get a lot of questions on Piazza where I look at the question and I'm like, but that's just lecture 4, or that's just week 5 lecture. But I know the lectures have a lot of info, and I know you have a lot of classes, and some details fall through the cracks. So I can understand that some people aren't up to date with every single detail and are having some of what sometimes from my perspective are obvious mistakes. But I know they're not obvious. You're doing this for the first time, so I should cut you some slack. Sorry guys, sorry folks. I'll cut you some slack, and I'll say that if you have any questions about memory, control flow, and functions, after our bit of revision today, please talk to your tutor about it. Tutors will help. We specifically told the tutors this week that if someone comes into a lab this week and asks about any of these questions, please help them as much as they can. So come into your lab with those questions. You won't get help for 3 hours straight, but you will get as much help as you need and as they can possibly offer. All right. About scanning the LED screen. So the LEDs on your microbit, where's a microbit? Here's one. It's not plugged in now because I unplugged it, but it's got these LEDs. But as you know from looking at the circuit diagram in the labs, the LEDs are set out in a matrix, which means that you can't display a whole image because the rows and columns are connected across, all the way across. So if you tried to draw a diagonal line on the LED, you would end up lighting every LED on the screen. So it's either all or none at some point. What you can do is activate any combination of LEDs in one individual row or column. And that's the trick. So this is the trick you have to do. So to display an image, you have to divide it up into rows or columns and display each one individually. And quickly, so that as you're going down displaying them all, eventually the human eye can't keep track of that movement. If it's fast enough, we just see it as a single image. This is how all screens work. All screens are scanning all the time. So it's not like this is abnormal. This scanning technique is totally normal for screens, television screens, LCD monitors, and everything. There's no sample code for this one. It's something for you to work out in your labs or in collaboration with your tutor or classmates. But we do have an example of how it works provided by Thomas, one of your tutors, who made this great video. So here's scanning an arrow. We're doing one column at a time to make this arrow picture. This is what it looks like slow, and then it speeds up every iteration. And then eventually it stops looking like an animation and just starts looking like an image. Eventually the camera shutter can't keep up with it anymore. And then it slows down again to individual columns. So take this as inspiration for how to draw images on your microbit screen, and hopefully this helps folks to understand the assignments. Someone's asked if you can use audio input in assignment 1. No, there's no inputs allowed in assignment 1, sorry. I'll just go back to the assignment specification. Please look at this very carefully. I've tried to keep a good balance between having an extremely long assignment web page and having good, complete information. You should not use any input peripherals on the microbit, so the LED counts as an input peripheral. One thing we haven't talked about much is this concept of a design document. You're supposed to include this design document, a maximum of 600 words, so not that long, about what your design is, how you accomplished it, and why your design choices were appropriate. Now you know that it's tricky to read assembly. So what's going to happen when your tutors read your assignment? They're going to probably look at your design document first to see what you're doing. And then they'll use your design document to help understand your code. So the design document is probably the most important part of your assignment in terms of communicating to your tutor or me, who might be marking some of the assignments, what you're supposed to be doing, and by extension, how sophisticated it is and what kind of a mark we should be giving you. Someone said, correcting, they're not doing audio input, they're doing audio output, which would be an extension, definitely. I think using sound, use the speaker to create interesting synthesized sound. That's an extension. If it's good, has to be good to get a good mark. You can see that the marking criteria, some of them are about your implementation in ARM v7 assembly. Some of them are about your design, your analysis of your design, and your communication. So half of these are going to be basically about your code, and the other half will basically be about your design document. But we do look holistically over the whole package to evaluate it. So make sure that your design document, it absolutely needs to be there. First of all, it's a requirement. And it has to be high quality. So to help you do the design document, we actually have a whole page about it, writing a great design document. So this explains a bit about what we're expecting, how to structure it. There's your three kind of sections would be the design, implementation, and analysis. Talking a bit about a balance between high and low level explanations, particularly because you've got a word limit. You can't go into huge detail about every single register and every single instruction. If I want the detail, I'll look at your code. What I'm looking for in a design document is a really clear, sophisticated description of how you accomplish what you do in your assignment. Then I would like, or it's a requirement to have this analysis section. So some explanation about why your design is a good one for your task. So are there any particular aspects of it that are where you've made a choice about how to do the implementation, which is better than an easier choice? So why is yours sophisticated? Why should we be giving it a good mark? That's what I want to hear from you in that section. Absolutely don't explain your code line by line though. That would be low level explanations. Please read this entire page. It's very detailed, but a lot of great hints about how to write a design document that we will want to read. Also, please look at the markdown syntax part. We much prefer that your document is well formatted. If it's not well formatted, obviously this mark about sophistication of communication is going to be low if I can't understand it because the formatting is terrible. That's part of that part of the marking criteria. Okay. Just a bit of a hint, extra information about the rows and columns of LEDs. Here's a cheat sheet to help you. You know this information, but it's good just to have it here in case you need it when you're coding. Okay, a little bit of a revision. I've just copied in some slides from previous parts in the course, just to remind you about things that are really important. Condition codes are important. Why are they important? Why is it really good to have a knowledge of condition codes? You know, col4. Col4 is the only one which is on P1. Why does it have to be on P1? Why? Why did they do it to us? Everything could have been on P0. I bet it's about routing. Like physically, there's no way to get the little wire from the microbit CPU to that LED without going out that particular side. So that's the best we can do. Yep, someone says the question was, why are these condition codes important? They're crucial in order to do if then else statements, while loops, for loops. Anytime we want to decide what happens in our code because of something, we need these condition codes. So I'll just remind you about this idea of the best if statement. So you might start your if statement, do some tests to set flags, maybe comparing two numbers, then branching to a then clause, which would be down here. If you're not taking the then branch, you automatically drop into the else branch, which is here, does the instructions, and then drops through the rest of your program. So if you need to do an if statement, this is the template that you might want to copy into your code and start to hack things up from there. Julian's saying that the port 1 pins are on the same side as P0 pins, but P1 pins are on the bottom. Maybe it was physically closer. Yeah, I don't know. I obviously haven't seen the routing, but maybe they had limited layers in the PCB. I don't know how many layers is in this PCB, but is it surely not just 2 layers? Anyway, I don't know much about PCB routing, but it's the kind of thing, we're talking about port 1, port 0 conflicts. It's the kind of thing where physicalities actually get in the way. You need a wire to go somewhere near an LED, and if there's other wires in the way, you're out of options. You have to do some compromise. So it might have been a compromise just to use that exact one on port 1. Another template for you. If you want to do a while statement, we would typically start with some kind of comparison, invert the conditional check for when to escape the while loop. Then you do your work, some while body. That's the body of the while loop. And then go back to the start. So first a check. That's not a very good template, but check or a test. Exit condition, then the body, then the loop. So if you want to do a while loop, you can copy and paste that in and start from there. And what about a for loop? Well, we had similar to the while loop, but a bit more complexity to set up the index register and get our for loop to work. Now, why do I keep saying this word template? Because I think when you're programming in assembly, you might be thinking about how you would code in a high-level language like Java, and then you kind of keep that in your head and then translate it into assembly as a smaller breakdown of the problem. So it might help to have some of these templates in mind to copy them in when you need to do something. And maybe you first of all copy them in and then optimize them after. What about a function? Well, here's a normal function template. Remember that the first priority things for a function is to have a label and a BXLR. That's what makes a function. Then We also had this idea of the prologue and the epilogue for a function to put things on the stack that we needed to keep safe and pop them off again. And we'll do a bit more details about functions in our worked examples in a minute. One thing that I'll talk about in our examples, you'll see more details here, but there's a concept called the frame pointer in functions and the stack. So there's an rn, oh yeah, I missed the dot size bit at the end. Whoops. Dot size, dot, 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 etc. There's a concept called the stack frame pointer. So if you remember, we might have the stack going down and our function starts there. You've got LR is there, saved registers, and then local variable storage or something. So now SB is here. But often when you're inside a function, you'd like to refer to things in this stack frame. If you're referring to them using SP, that's tricky because SP keeps moving. So often you keep another record of that location in memory, and that's called the frame pointer. So it points to the base of that function's stack frame. That means that you can find a local variable, because you might have a local variable here, maybe it's called A, and A might equal FP plus 8 or something. I'm just making that up, but you could easily access A with an offset from FP if you're using local variables in the stack. We'll do an example in a bit. You can't do this with SP because SP keeps moving, so you have to have another register dedicated to being the frame pointer. And often, just when you start your function, you would push FP, because that would be the FP from the previous function, the stack above you, the frame pointer above you. It needs to be pushed and restored, popped off at the end of the your function call. Function, there we go. That's a bit rude, sorry. Didn't mean to do that. It was an absolute typo. I'll fix that very quickly. Toolchains and compilers. If someone's clipped that on Twitch, you have to delete it. What is a toolchain? A toolchain is a collection of programming tools that are used one after another to create a program. So this would be part of the way that we build software is to have collections of programming tools working together. And the there's some people laughing at me. I'm laughing at myself. That was embarrassing. That's the one word I would never wish to say on on a stream. You're using these tools every day when you're developing in COMP2300. This chain of tools. And we said at the start of the course, just reinstall your toolchain, Like, it's built into our extension. Reinstall or update toolchain, which downloads all of these tools to help you compile your code. But what are they? And we're going to just talk a bit about what they are and then play with them a bit in the abstract in some sense. So when you build your assembly code in VS Code, there's actually 4 GNU tools being used. These are from a bunch of developer tools as part of the GNU project, GNU project. The GNU project goes back a long way. It's an attempt to create some open source tools that would replicate tools available in an operating system called Unix, which is venerable now, very famous in computer science. Unix was a commercial operating system, but when it first emerged, it was sort of treated as being free software. So when it became commercial at some point in its history, there was a response from the community to say, no, we want these tools to still be open source, we want to share them freely. So the idea of open source coding was invented to capture this idea that we should have software where we can share the source code for it around and improve it as a community, rather than everything being about commercial interests. So the GNU stands for GNU's Not Unix. It's an an alternative to the Unix operating system and collection of tools. And of course now GNU is old as well. It's had its own history of development. So all of these tools, Make, GCC, LD, and Obj Copy, are part of the GNU Bin Utils, or GCC toolkit. And there's one extra tool we also use called Openocd. Where is it on my computer? People are going to cancel me now. They're claiming in the chat. I'll edit it out. When you installed the COMP2300 VS Code extension, all of these tools were automatically installed in a folder called .comp2300, which is in your home directory. So I was going to look in my home directory, .comp2300. And there are 2 folders that contain most of these tools. That folder has Openocd in it, and the other one has a bunch of stuff, including all of these important GNU Bin Utils tools, of which there are many. If you have a Mac OS or Linux computer, you already had the tool called Make, which helps define how these tools are used together every time you click Build and Upload on VS Code. And if you have Windows, you installed Make in the first lab. So how does this work? Well, Make is the one that runs whenever you hit Build and Upload. You know it's running Make because, whoops, I'll put that over my face. It's executing task Make. That's running Make. So Make is called a build automation tool. It runs every part of the build process in sequence. And it's also clever enough to know if you've got many source files, which ones have been updated and which ones need to be built since the last time the build products were created. GCC is part of the GNU compiler collection. It used to be called the GNU C compiler, but now it has support for many languages. And that turns assembly commands into CPU instructions. So we could actually use a simpler command called AS, which is GNU assembler. But GCC is a bit smarter, so it's actually a little bit more useful to use GCC. I'm not sure of every detail there, but it turns out it's a good idea just to have GCC. I've tried things with AS, and you have to add some extra bits and bops. I will try a function with more than 4 parameters in live coding. I will get there. So we do use GCC to go from assembly into the CPU instructions. Then we need this tool called LD, which is the linker. So what that does is it takes your CPU instructions and then all of the data that is needed in your program, in the .data area, and it makes them into a correct kind of memory mapping between them. So LD knows about the memory layout of the microbit, where it needs things to be in memory. So it's allocating memory locations for each variable and each line of code in your program. Then we have another kind of binary encoding tool called Obj Copy. So LD produces a file called an ELF file. I forgot what that's called. Extensible Linux format, I think. ELF binary format. Executable and linkable format. Yes, sorry. Another terrible mistake for which I should be cancelled. Executable and linkable format. It's a file format for things that come out of a compiler, basically. But we want Obj Copy to remove some of the extra info there and just give us the binary data in a big splat, just to be mapped directly into the microbit's memory. So that's what Obj Copy is doing for us. Then when we got the output from Obj Copy, we've got a .bin file, we use Openocd, which stands for Open On Chip Debugger. That helps us upload the .bin file to the microbit, and it also allows us to do this step-by-step debugging in communication with VS Code. So VS Code's not running this code. Openocd is talking to the microbit, and the microbit is running the code. So when you click down in VS Code, that's sending a message to Openocd, and Openocd sends a message to the microbit to do that step through that code. It's all really clever stuff. really cool how these things work together. There are other options. You don't have to use Openocd. You can use the GNU Debugger. It's not going to connect nicely to VS Code, but there are ways to make it do that if you want. You can use different debuggers provided by different commercial organizations. I think there's a debugger provided by Keel that is often used with ARM chips for debugging programs typically written in C, but we use Openocd because it's open source and it works nicely with VS Code. Yep. So, what else was I going to say about these? I think I've got a blog post somewhere, or maybe it's half written, where I show how to use AS, LD, and just the GNU debugger by themselves. So GDB is the GNU debugger. So I might post that and send you a link to it sometime so that you folks can see how to do it and you might like to try it. But it's not really, it's COMP2300 adjacent. It's not core material for the course. So now we know this. We've got all those tools. But what about this GCC thing? It's called a compiler. And what does a compiler do that our assembler is not doing? What are the extra stuff that it adds to allow us to code in a high-level language as opposed to in assembly? So what you could think about what a compiler does, and this is not the whole story because you might want to take a course in compilers as an advanced subject, 3rd or 4th year level. But you can think about a compiler as being kind of like an automatic template filler. So if you write if in your code, if you write if, or if you write a function, or if you write a while loop, the first thing your compiler might do is kind of fill out one of those templates to turn into the best assembly code, or just the instructions, or whatever intermediate representation the compiler uses in between high-level programming and machine instructions, of which there are many options, because compilers work in all kinds of interesting ways. But they do something to turn high-level programming constructs into templates that can then be turned directly into machine code. So there's a lot more details to happen here, but basically that's what a compiler is doing. And we can actually, when you're programming in assembly, to be a good assembly programmer, excuse me. Sorry about my voice today, I'm running out of it. To be a good assembly programmer, you need to have a great understanding of those high-level concepts, and then you can optimize after that. Okay, here I am. So how are we going to test this out? We'd like to see what these compilers are doing and see some of these templates in action, right? That would be a good idea. So we're going to do some experiments with copying and pasting to see how this kind of templating works. And the tool I'm going to use is a website called Godbolt. So Godbolt's a guy's name. I thought it was like some kind of, I don't know, the Godbolt might be like the secrets of the universe or something. But this website, this is so cool. This lets us write code in C++ and turn it into ARM assembly. Let's make a little function. Void int I equals 0. So there's some C++ code. If you don't know C++, just squint and it looks like Java. So it's a similar C-like language. You know Java from 11.10, hopefully. So here is this, I'm going to call it boring function. What does it do? You can select individual lines to see which lines are actually doing the work. It does a lot of stuff, doesn't it? For one little line of code. But a lot of this is actually the template, and it's not the main part of our code. So I might try something else. Here's the main part of our code is just making a local variable and setting it to 0. So here's what it does. It moves 0 into R3, and then it does something interesting. Because it's a local variable, which might need to be used later, it puts it on the stack. That's where I said we would store local variables on the stack. And it puts them on the stack not relative to SP, it puts them on the stack relative to R7. And in this case, it's using R7 as the frame pointer. I don't know why it uses R7 and not R11. I'm not sure what what version of ARM this thinks it's compiling for. I could probably add more GCC stuff there, but there you go. So that's cool. We'll go through its stack work here. First thing it does is push R7. So it knows it's not using LR, so it's not trying to push LR to do anything. But R7 is being used as the frame pointer, so it does have to push that. That was the previous function's frame pointer. Now it's going to make some space on the stack. It'll make 12 bytes of space. Then it's going to set R7 to be the current, the base of that area. So it's choosing the bottom of that kept space to be the location of our frame pointer. Then we do our activity. We move 0 into R3 and store R3 somewhere back on that in that stack space that we've just cleared out for local variables. Then we don't do anything. Nop. This is the rest of the function is do nothing, and then we basically getting our stack back to the way it was. So we're restoring R7 to where it was, or restoring SP to what it was before we started the function, and then loading back the stack pointer, which we'd just, the frame pointer, which we'd stored. So that's the pop is this stuff, popping off that local variables and the R7 storage, then BXLR. So that's a really boring function, but you can see that when it's optimized, not optimized code, it's doing a lot of work that it doesn't need to do. What if we do a while loop? While, I'll make some variables first. Int I equals 0. Got to do a semicolon. Int a equals 1, for instance. While I less than 10. Do some stuff. I don't know. A equals a plus I. And I might return a. All right, we've got much more complicated thing now. We've still got this concept of using R7 as the frame pointer here. First thing it does is just set up some stack space for our local variables, still using that same 12 bytes. Setting up our new frame pointer, R7. Okay, we're going to store local variable for I, which is going to be at the frame pointer. That's this bit, those two lines. Then we're going to do our local variable A and store that 4 bytes up in the frame. Now we do our while loop. And it's got a good trick here, a good little optimization is to put the body of the while loop, or start the body first. Well, start the test at the, sorry, put the test at the end and start that first. This is the test bit of code. I can't edit the read-only editor. Can I change it, please? I want to edit it. No. This is my testing part. It loads up I, compares I to 9, and then runs .l3 if it's less than or equal to 9. So that's less than 10. I don't know, I would have used BLT10. Why would you want to use 9? Anyway, I feel like it's more clear to use 10 if that's what I've written in the while statement. But compilers are going to do what compilers do. It might have some good reason to do that. Then we do the body of the loop, that's L3. .L3, loading up. Oh, that was A. Yeah, A is at R7 plus 4. Loads I, add I to A, and then store A back in its location in the stack. So loading something off the stack, loading another thing off the stack, adding those two numbers together, and then storing it back on the stack. All stack work. Really great to see how that works, isn't it? In a real situation. Real. It's a pretty dumb program, but it's still doing it for us. So what's the last thing it does? Eventually it will come down to this. Oh, we don't have to loop back to the top because it'll just drop through after that loop body to the next test. Eventually I will equal 10, so we drop out of the loop. We skip this bit and we get down to the return A bit. So to return A, we're going to load R7 plus 4 into R3. Then we mov R3 into R0. As you remember from the ARM procedure call standard, R0 was a return location. Then we restore the stack back the way it was and BXLR. Now that is pretty cool. That's my catchphrase. Anything else we want to try here? I'll try something cool, which will be to say, bringing in some numbers from as inputs. So we got 4 inputs in our function now. Can you see all those stores on the stack? R0, R1, R2, R3. 4 inputs. And we know from the procedure call standard that you're allowed to use R0 to R3 as your arguments. So the first thing it does is it stores those on the stack so that they're nice and safe within our stack frame in this instance. What if I add another one? And I've added another one, but we're still only have R0, R1, R2, R3 there. Where's D stored? Where's D stored? I'm going to use D so we can find out where it's stored. It was on the stack all along. I said last time we were here, I said that when you're using arguments as inputs for your function, you're allowed to use the first 4 registers as your arguments. And then for other arguments, you're going to have to use the stack. So this is just what the GCC, the GNU compiler collection, has done. It's using all of the regular registers as its regular input input parameters. It's storing them on the stack just to use them as local variables, and then its other parameters, it knows they're on the stack, but they're on the stack outside of the stack frame. They're at the further behind. So R7 was at the the lowest address in the stack frame, and it was going back 20 was the amount of space it made, and it needed to go back to 24 outside of the above where it had stored R7. So that was 20 down from the push of the previous frame pointer. Above that frame pointer, it had stored that int d. So that is cool too, isn't it? We replace all the stores with push. Someone says, can we replace all the stores here with push? No, because, well, you could, but in this code, it's already moved stack pointer. So it's making space. That line is the making space line. And then these lines are this line is the setting the frame pointer line. And these lines are the storing things on the stack line. Now, I'm not saying you have to do everything the way that GCC is doing it. GCC has its own templates, its own best idea of how to organize code. And in fact, we could probably get, see what happens if I change it to --03, which optimizes the code. In fact, the code can be really optimized into almost nothing because I don't know what it thinks it's doing here. Anyway, R0-9. This optimization starts to remove all of the information that was supposed to be using. I'll try the optimized version of the previous function I had. This one, it just does nothing so far. It seems like that's not going to work, so I'm not so sure about how that works. 01. Maybe I'm not doing anything useful. Anyway, you can certainly, instead of making space and then doing the stores, you can certainly use push. But the point of what I'm showing you here is that there is a template to the way that compilers are creating your code and organizing it so that it makes sense. So if you think of a compiler as filling out templates and then doing optimizations, that's kind of what a compiler is doing. So when you're running your assembly code, you should kind of be a compiler. First, use a template, and then make optimizations to make it better. So that's a thought. Where are we at? I'm just going to grab a bit more water and then I will come back and have a look at this demo. So excuse me for a second. Okay, and sorry to whoever it was who thought that my lectures was a bit slow because of waiting for... Oh, I is never incremented. That's why my... There we go. I is never incremented. It's going to run forever. So, yeah. I equals I plus 1. Another classic Charles problem. Got to increment your... Oh, there we go. So, the optimized version of our function is just to load do one instruction, load in a constant, and exit. So, the unoptimized code does exactly what we told it to do. And the optimized code is like, wait a minute, that's just returning a constant. So I'm just going to return the constant and save you like 50 instructions. 25 lines of storage. So you can imagine that over a program, when your compilers are doing optimizations, they're saving you time and they're saving you storage space. And if every one of your functions can be optimized to make it much smaller, that's a lot of saved storage space. So compilers are doing a lot of great work for us. But in this case, it's fun to see what the compiler does when the optimizations are turned off. And the answer is a lot of storing stuff on the stack, basically. Storing things on the stack and getting them back again. Okay, table branch instructions. You might have seen one of these weird ones in the resource section. Assembly cheat sheet. Table-based branch. What does that mean? Table branch. What? What is all this? We're going to have a look at the table branch instructions. TVB instruction. There's probably there's many examples that I clicked on because I'm trying to remember about how to use these things. So the idea of TBB is to let us branch relative to the PC, the program counter, forward using a table of single byte offsets or half word offsets, where we have two inputs. RN is going to be a pointer to the table, and RM is going to be an index into the table. So at this point you might be thinking, well, that just sounds like a lot of nonsense. Why would I ever need to do that? Well, you might like to try it when you realize that what it can give you is something like a case statement in a high-level programming language. So what we're going to do, I'll go into here, make some more space for myself. Okay, there's my old recursive function from last time. What? Type main, that should be type factorial. I'm going to make another function. I haven't installed the snippet for making functions. By the way, did you see on Piazza, Benjamin pasted in a way to help you to add a snippet in for functions? It's always a bit beyond me to add snippets into Visual Studio, but thankfully Ben has our back. Case example. Okay. BXLR. So I'm sorry, I'm setting up a little bit of boilerplate here. Okay, we got it. So what are we going to do? What I want is some kind of thing with a case statement on R0. And if you don't know what that does, it might look something like this. Do something. I'm just making this up, but it's a way of doing a very efficient if then else, basically. You have an integer in an input argument, and then you've got different cases for each number in that integer. Again, 3, etc. Right, so it would choose to run different lines of code based on the location in R0, or the number in R0. And we can do exactly that with this thing called TBB. So, cases in R0. The way you use this is to say TBB PC R0, and now it's going to branch forward from the PC by a certain number of bytes. So you might think, or it's going to look for a byte of information a certain number of bytes away from PC and use that as the location to branch to. Sorry, I'll try to write this down. TBB gets a memory location stored a certain number of bytes away from PC. I'm going to say certain R0 bytes away from PC and branches to that location. So I'm going to have to give it some places to branch to. Give it some places to branch to. We'll go case 0. I'll make a couple of cases. Case 1, case 2, case 3, case 4. So I've got 5 different cases. And these cases are going to do something different each time. I'm just making something up. They could do anything you want. How do you know how far away from PC to go is the question someone's just asked me. I'll show you in a minute, but we're going to just set up my cases so that come on Siri. People can send me things on my phone, or Teams messages go to my watch, and then Siri thinks that I'm talking to Siri, but I'm not. I'll do this as well.
There's nothing playing on this
There's another one happening. Too many Siris. Okay, and then it needs to be exits case example. I should have copied more things at once. And one last thing, I'm just going to make sure that I've got a different number in R0 each time. Okay, and then nope, there. So I've got all my cases. So wait a minute, what's TBB going to do? How does it know how to get to case 0 when 0 is in R0? We need to put in a table of memory locations, or offsets actually, it gets an offset stored R0 bytes away from PC and branches to PC plus offset. So this memory location there, it's not very far from PC, is it? So PC should be here, line 15, and that memory location is like 1, 2, 3 words away from PC. So it's not going to be far. I guess we could enter it in by hand if we wanted to. We don't want to because that would be crazy. We're going to use the assembler to help us work out these locations. And we actually want to put I'm looking at a thing on my other screen. I always need to have a reference for TBB. It's too complicated to do without a reference. Branch table. I'm going to have my branch table here, and I'm going to say case 0 minus branch table. So that's the distance between this label and this label. This label has a lower one, so it makes sense that one's second. Now, the trick is that we don't need to have a number of bytes away, we actually need a number of half words, because if you remember, all of the instructions in the instruction stream are aligned to half words. So this calculates the number of bytes in between, and we're just going to divide it by 2 to get the number of half words. I don't think we need that bracket around there. That should be fine. Okay, so that gets us our first case. Then we're going to do that a few times. One, two, three, four. Okay, now we're getting somewhere. Now we're getting somewhere. We have TBB. It's looking for something R0 bytes away from PC. It finds a byte of information, and then it does a PC relative branch to there. The one last thing I need to do is type .align to make sure that my next instruction is aligned in the instruction stream correctly. So this should work, I hope. We've got R00. I'll save it and I'll run it to see if this is actually going to get me somewhere. Set R0 to be 0. Go into my case example. TBB PCR0 gets me into case 0. Load up OXA. Exit case example. Oh, then we go back here. End loop. So I need to have something at the end of my main function so I don't drop back in anymore. Someone's saying that's a lot of work. It is a lot of work, but once it's there, it's done. And you've got a really cool case template. So if you wanted to use this for something, you could just copy in the template and change some things around. And it's then a really clear way of defining what you might want to do. And I could imagine that one might want to do something like have a function called get call address or something, right? Or turn on LED number. So you could have some case statement where you give one argument for a column, one argument for a row or something, and you've got a cool case statement to work through that. And maybe something like this would be useful. I don't know, I'm not giving any hints right now. Why should it be branch table? Well, it can be anything, that can be anything I want. This stuff is calculated by the assembler and ends up in the instruction stream as just a number, a .byte. So branch table and the case 0 labels are just giving me something to use for the assembler to calculate the value of these offsets to get to each of these locations. Try another one. Move R03. Got 3, go into the case example function, TBB. I'll tell you why in a minute. Someone's asked another good question. TBB, PC, R0, so it's going to look 3 bytes after that. 0, 1, 2, 3. Get that offset and then branch to there, and it works. More R0, OXOD. So let's go back to the definition of what this is. I guess I really want to look in the reference. Instruction details. Alphabetical list of all the instructions. It's T, sorry, this. Okay, table branch byte causes a PC relative forward branch using a table of single byte offsets from PC. So a byte can only handle up to 256. 256, so that's a small number. You know, memory addresses are 32 bits, not just 8 bits. 1 byte is 8 bits. So we can't store the whole of a single memory address inside one of those, the entries in that table. So we have to use a smaller way of doing it. We only use the offset, not the full memory address. So it would be nice if this table could just have .word and case 0, right? That would be the memory location of case 0 stored as a word. But it's not word, a word table, it's a byte table of bytes. So it can only store a few offsets, a small range of offsets. So these ones are all within range. They're within 256 half words. Adam Rowland asking me questions again. What is this, 2020? And we're shifting PC by the difference. Yeah, I know. I thought I was telling you that. Yeah, so back to the explanation in the thing. Table branch byte causes a PC relative forward branch using a table of single byte offsets. So the table has to be bytes, so that means we can't offset by very much, and it's a PC relative forward branch. So we've got to find the distance between PC and the location we want to get to. So the PC here is that location. This is going to be PC. See? Offset from PC to case 0. Stored in half words, not in bytes. So many questions. Everyone's perked up now. I've done something interesting and they're not sure why it works. So we store this offset not in bytes, but in half words. We store it in half words so we get more range, because if you're only in bytes, you can only go 256 bytes forward, 255. If you store it in half words, you can go double that. And we know that all of the instructions in the instruction stream are on a half word offset because they're minimum 16 bits. There's no instructions that are 1 byte in length. They are at least 16 bits in length, which means we can refer to an offset by a half word and be accurate to within one instruction. The dotted line is needed so that the next line of code is on that half word offset, not on the wrong one. So it needs to make sure that after our random list of bytes in branch table of bytes in the instruction stream, we start on the correct even numbered offsets. The branch length is twice the value of the byte returned from the table. The branch length is twice the value of the byte returned from the table. In the architecture reference manual, I know it needs a reference manual, but you have to believe it when it tells you things. Like if it has a sentence here, the branch length is twice the value of the byte returned from the table. That's actually important, right? That means that the branch length is not the same as the byte returned from the table. It's twice its length because it's only looking at the half word. It's only looking for instructions. It doesn't need every byte. So if we want it to branch to case 0 minus branch table, we need to store in the branch table case 0 minus branch table divided by 2. The reason why is to give us more range, but as to like morally why we should do this. Morally, it's telling us that that's how it works, so we have to do it. I know it seems like a lot of work, but isn't that cool? It's really neat. Imagine if you had to do like a compare for each one, and then compare for 0, oh, not 0, drop through the next one. Compare for 1, oh, it's not 1, drop through the next one. Compare to 2, right? That's really inefficient. No matter what R0 is, it always gets, in one instruction, it gets to the correct place. Now, no matter what R0 is, in one instruction it gets to the correct place. I'll write this down. Why is this good? No matter what R0 is, well, between 0 and 4, it gets to the correct place in one instruction. I believe that TBB is a one instruction, a one clock cycle instruction. Programmer's model. TBB. There we go. Oh, no, 2 plus P. Well, it's not one instruction, okay. It's the number of instructions plus something. What's P? I don't know what P is. Oh, the number of cycles required for a pipeline refill. Okay, so that takes in 2 instructions plus, in 2 to 5 instructions, or 2 to 4 maybe, I don't know. 2 plus P. Instructions. P is num instructions to refill pipeline. Typical for a branch. You need to refill a pipeline. All right, well that was fun. Anything else? What else should I do? Someone had a good question. I've got another idea for a demo. Oh, the bit field instructions, they're a bit crazy. I'll do this other one, a function with stack parameters. What else did I have? Recursive Fibonacci. Ooh. And then there's some further reading there. So if you have to go, you can catch up with this on the recording later, but where was my previous good question? Making a function that has more than 4 parameters. Well, I think we've done that in the Godbolt work, but I'm going to do this for the frame, just using the stack for a function anyway, just so that we get clear on that. Stack function. Call it stack function, and at the end of it, we go with that. Stack function. What does every function need? It needs to start with a label, and it needs to end with BXLR. That's what every function needs. So this function is going to take one argument from the stack, and it's going to return one value, same place on the stack. So at this point, our argument is actually the last filled place on the stack. So last place on the stack. So argument is at SP plus 0. That makes sense. The SP always points to the last filled place on the stack. So if we want to get our argument, we're going to load it up this way. Loader R0 SP. All right, that's easy enough, isn't it? But we might want to store some other stuff on the stack before we we do anything. So how are we going to do that? Oh. I guess it's our right to overwrite R0. So we could load our local variable in, and then we could push LR, R11, LR, 4, 5, 6, 7, 8, 9, 10, 11. Someone's texting me something again. I'm going to think this through as I work it out. Oh, Adam's answering someone else in the chat. Thank you very much, Adam. Great answer. I have to think about this. I might have to go back to Godbolt to remember how to do it. How do they do it on Godbolt? First thing they do, push FP. Okay. I suppose we could just remember where it is. Well, we load up our first value there, that's fine. Our argument from the stack. Do some work, I don't know, we'll multiply it by 2. How about that? LSL, R0, R0, 1. That's easy. We don't really need to do all this pushing, do we? So we could, after our function is done, we'll pop off and we'll store back that value where we found it. So because I've got a push and a pop, I didn't need to do all that, not do some other stuff. But I do need, if I push anything at all, I need to make sure it's balanced out at the other end. And you could see in those Godbolt examples that the compiler was making room on the stack, and then before it exited the function, it got all that room back and put SP exactly where it was. So if I've pushed a bunch of stuff on the stack, R4 through R11 plus LR, I need to pop it off at the end. Whoop. And then the last thing I do is change that value on the stack. I could also do that another way. I could say up here, store R0, but it's going to be SP plus a lot of numbers. So how many things have I got on the stack here? 4, 5, 6, 7, 8, 9, 10, 11. 8 things plus LR, that's 9 things. So how many bytes is that back on the stack? 9 times 4 is 36. That's easy. SP 36. So that's going to store it back on the original stack value. So I'm reading questions. When I was using the stack, I stored some registers with push LR, R4, R5, and then I went to pop it using both pop LR4, R5 seemed to work. Compiler is smart enough to know what I meant if I put the same registers in both commands regardless of order. That's a good question. So why would it be, if you do pop R1, R3, R5 and pop R5, R1, R3, it's doing them in the same order. Does anyone know why that's happening? I can help find out why by looking in the reference manual. The reference manual, it has all the answers. Where is it? That's not it, there it is. We'll go and look at pop and see why it's doing that. Push and pop. So, if you're doing pop and you've got R1, R3, and R5, the way that's stored is by setting individual bits in this instruction. So the order that you put those registers into the assembly code doesn't matter. This instruction can't store the ordering. It can store which registers you want pushed and popped, but not what order they're done in. They always do them in the same order. So it always pushes them in the order that it's popped them. Or always pops them in the reverse order than it pushes, so that it works out if you do a push and a pop with the same particular registers. I guess I should test out if my stack function thing works. So I'm going to I'll push something, mov R0, 5 into R0. I'll put that into the stack, push R0. Then I'm going to run my stack function, and then I'm going to pop back in Y0 to see what I've got. Okay, hopefully this works. We'll find out in a minute. Hopefully it doesn't crash. No crashes so far. 5 in R0, we go into our stack function, load 5 from the register. Didn't need to do anything, but I guess I'll put something in here but just to wipe it out, just to prove to you that it's doing the correct thing. I'll put it into R6 or something. That's better. Pop R8. I'm just using random registers just to demonstrate to you what's going on. So R6 is 5. We go into my stack function, and it's going to load that 5 from the stack into R0. Well, there it is. It's loaded it, but it hasn't changed the stack. Now we change the stack, push a whole lot of stuff on the stack. We multiply R0 by 2. LSL R0, R0, 1. Now R0 is 10, or OXA. Now we pop all our stuff back off the stack, and then we store R0 back on the stack. We're not changing the stack for that one. Then BXLR, back to where we started, and we pop R0 into R8, and there it is, OXA, or 10 in decimal. So that's 5 times 2. So it seems to work, our storing values on the stack for our function. I'm glad that this branch table thing has really spurred a lot of conversation in the chat. It's a really fun concept. Okay, we did a value. We did function with stack parameters. Maybe I'll do recursive Fibonacci so we can test that one out. Last one. Make another function. Fibonacci. Or Fibonacci. I had an exam question called Fibonacci, which was something that was like Fibonacci, but not. Okay. Fibonacci. So if you remember, the Fibonacci sequence is like this: 1, 1, 2, 3, 5, 8, 13, etc. So our argument will be in R0. If R0 equals 0, return 1. Yep. If R0, I'm going to just say is 1, return 1. Else, return Fibonacci R0 minus 1 plus Fibonacci R0 minus 2. Neato. So first we'll take care of our base cases. We could use the stack. That would be fun. Push R0 and LR. Probably don't want to pop R0 and LR because it's going to overwrite my other stuff. I'll pop it into somewhere else. So whenever I need that original number, I'm going to have to load it back off the stack, just so you remember that. You know, maybe I'll do that only if I need it. We'll push LR just to start with. Okay, here's my first comparison. Compare R0, 0. And if that's true, we go to the base case. Label. Well, it's got to have a label down here, which is exit fib. Compare R0 to 1. If it's the same, I'm sure there's easier ways of doing this, but I'm just doing it in a simple way so it's obvious. Check for base case. And if either of those is the case, we mov R0 1. And get down to the end. B exit fib. It's a bad form to use a register as a get out of jail free card when the stack is messy when getting previous LR locations. Register. I don't know what you mean by that. You might have to give me more detail about that question. Is it something I've done, or is it something you've done and you're asking me if it's good or not? I guess if it works, it's not bad. So if everything is fine, everything is fine. But something is bad when it breaks your program. So that's the real problem. Now I've got to do the recursive case. So I'll make a label just so I know. I should call this fib base case or something, otherwise I'm going to have labels on labels. Fib base case, fib base case, fib recursive case. And I'm going to do that here, so it just drops through. I don't need a label, but I just wanted to have one anyway. And I don't need a branch there either. It can just go straight through. So this time it now needs to return that. Whew, so we're going to have to do some stuff. At some point, we're going to have to say BL Fibonacci and another BL Fibonacci, aren't we? But we have to set up our parameters. Sub R0, 1, BL Fibonacci. I'll put it in full, I guess. R0 equals R0 minus 1. What about we use the stack? Push R0 onto the stack. Okay, now we change it. We're going to use that function, Fibonacci. I'm going to mov store output in R1. Okay, this so far so good. We're going to get back our previous R0. Pop R0. R0 equals R0 minus 2. BL Fibonacci. Now the value of that Fibonacci call is an R0, so we can do add R0, R0, R1. That's adding these two together. And then we can branch to exit fib. So now we've got a tricky thing. Is this going to work? And you might say, well, it's confusing enough at this stage that I have to presume it works. But there's something else we've got to do, because when we stored the output in R1, whoops, the next Fibonacci call could overwrite that. R1 was one of those caller save registers. So we're going to need to pop R0, but then we'll have to push R1. And at the end of that Fibonacci call, pop back R1 so that we have it stored. Store R1 safely. And we know that it's going to get overwritten because we're running the Fibonacci function, and our Fibonacci function uses R1, so it will definitely override it. Yeah, I think this should work, hopefully. I'll try a few things. Mov R0, 0, BL Fibonacci. Oh wow, no problems detected. Oh, nope. Big problems detected. What have I done wrong? Error missing expression, S54. Oh, whoops. Well, 0, 0. That's what it does in the base case. That's what happens when you forget to write your stuff in. Okay, we got 0 in R0. We go into our Fibonacci, push LR, compare that to 0, go to the base case, mob R0, pop. Oh, we end up back down there. I forgot to BXLR, the main thing. The main reason a function is a function. It definitely needs BXLR. Man, you have to be so careful with assembly, don't you? To make sure everything is exactly right. Otherwise it will break in all kinds of ways. Push LR, compare R0 to 0, go to the base case, move 0 to R0, pop and return. Okay, so we're happy. Just going to put a break point there so I can skip it. So 2 should return 2, right? That's 1 plus 1. So in a recursive case, push R0, return 1, do BL Fibonacci again, base case should drop down, yeah, store the output in R0. That has to be 1. Whoops. Storing the wrong immediate values. I'm at the end of my 2 hours and I've gotten tired, so I'm making big mistakes now. I wanted to get through this because I promised, and I don't think I'm going to lecture on Thursday. I'll give that time back to you for assignment doing, and then, so no lecture this Thursday, and we'll catch up again in week 7 with data structures. That's the base case, we get a 1. Hooray! So we're storing that output in R1, that's good. Pop back our R0, push R1 on the stack, change our R0, go into the Fibonacci function, exit the Fibonacci function. We've got an R0, 1 in R0, and a 1 in R1. And then we add those together, we get 2, and we exit. Okay, so 0, 1, 2, 3, 4, 5, 6. We should get 13 if I put 6 into the Fibonacci function. And this time I'm going to skip over it because it's too annoying. 6, and then I step over. And it works, I get 13. There's a lot of function calls in that version of Fibonacci. There are more efficient ways of doing the Fibonacci algorithm, but that's a very typical kind of recursion, doubly recursive way of doing it. Folks, it is 4:15. I'm going to call it a day. I'm going to call it week 6. We've had a lot of revision today, a lot of high level talking about how to be a good student in COMP2300. Remember that you have this extension until Monday or until 9 a.m. Monday for your assignments. I hope that takes the pressure off. If you finish your assignment by the end of this week, don't feel like you have to do more work. This is just a moment in time. It's just one assessment piece. If you've got a moving, engaging little animation on your microbit, that's a great assignment. You'll likely be at least in the good category for marks there. So if you find anything that you need to put more effort into, I would say that most people need to look twice at your design document, because that's a bigger part of this assignment than it has been in your assignments in first year. The little reports you did tended to be a lower proportion, if I'm correct. That's my understanding of how those assignments typically work. Your design document is worth half this assignment, so make sure it's good. Look at it twice, make sure it's pretty, make sure the markdown is perfect. If you want to include an image to illustrate something, do so, that would be cool. But please try not to stress too much about this. The assignment is supposed to be a nice challenge moving on from your lab work, not supposed to destroy your life, basically. So it's, I think most people should be able to provide a good response on that basis. So I don't believe there are any more questions, in which case, what? Restream and Microsoft Stream broke. Anyway, I don't believe there are any more questions. So in that case, I am going to call it a day when I find my remote control. I will catch you folks in week 7. Keep up the good work on your assignment. Make sure you study for the mid-semester in week 7. And I'll see you folks in a few weeks. See ya.